So this is the last chapter in the course. It's on Faraday's law. I've done a number of videos that will help with some of the problems on mastering physics. But basically, Faraday's law is the law of electromagnetic induction. Looks like this, where phi is the magnetic flux, exactly analogous to the electric flux. It's basically the number of magnetic field lines passing through any given area. So what this Faraday's law says, this is EMF, voltage in volts. N is the number of turns of the conductor in which you are inducing an electric field, which is going to cause this voltage. And then this, of course, is the time rate of change of magnetic flux. So this is magnetic flux. And unlike electric flux, it does get a fancy name. The units for magnetic flux are Webers. And so from this definition, you can see that a Weber must be a Tesla times a meter squared. Okay, so in order to get this induced voltage, you have to have changing flux. And another way to write this magnetic flux is that it is the dot product between B and A. So it is B, magnitude of B, magnitude of A cos theta. Now, those are possibly three different variables: magnetic field, area, and angle. So when you take the derivative of this quantity, you have to use the product rule. So it would be the first two times the derivative of the third plus first and third derivative of the second plus second and third derivative of the first. Okay, so that is the general derivative of magnetic flux. So what does this mean? This means if you have a changing angle between the area vector of the loop in which you're inducing the magnetic, inducing a voltage, you keep the area constant. This would basically be rotating. So what this means, changing angle, this is a rotating coil. And that's the principle behind generators and motors. So this is rotating a coil in a B field. So the area of the coil stays constant, the magnetic field stays constant. If you twirl the loop, you're going to induce an EMF. This would be keep the field the same, keep the orientation the same. This would be a shrinking or stretching area. So this would be changing the area of the loop. An example of that would be the rod on the rails. So for example, if you had a rod and there's a magnetic field everywhere here, and you take this rod and you move it over, this is the loop, this is the area here. That's going to change as that rod slides over. So that's how you get that term. And then this would be if you just literally have a changing magnetic field. And I've done an example of that, a video of that, where you're given B as a function of T. So this is just changing magnetic field. Now you almost never have all three of these going on at once. You either have a rotating coil, or you have a changing area of the loop, or you have a changing magnetic field, not all three at the same time. Okay, so remember this, the angle theta is between the normal to the loop and the magnetic field. So in this case, theta would be 0. And that's quite well laid out in the video you have on mastering physics. Okay, so another example of how to induce an EMF is this example of, it's called motional EMF. And what that means is if you have a magnetic field, so this would be B into the board, and take a metal rod and you move it in this slice through the magnetic field lines with some velocity V. what happens to all the electrons in this rod is they feel QV cross B, the magnetic force. And so if you do QV cross B, positive charges would go up and negative charges would go down. So this would be the force on the electrons. And this would be F equals QV cross B. So if all the electrons now move down to the bottom of this rod, you're going to leave behind a positive region at the top of the rod. So as this moves through the field, you get an accumulation of negative charge at the bottom, down here, and positive charge at the top. Now this creates an electric field in the rod in this direction. And that electric field is going to do the exact opposite thing that the magnetic field did. It's going to try to pull these electrons back up. And so you have these two opposing forces, the electric force from the separation of charge, the magnetic force from the motion through the magnetic field, and there will continue to be motion of these electrons until those two forces balance. So when QE equals the QVB, that's when you'll reach equilibrium. Now the electric field, we know this is the length of the rod, L. Voltage, so there'll be a potential difference between the top and bottom of the rod. The voltage is equal to the electric field per distance, per length. Okay, so this is voltage. And so it means that I think I got that back. Sorry, I got that backwards. D times L. Okay, so if we put in that the E is V divided by L, voltage per length is V times B, it means the voltage is B times L times V. And this is called motional EMF. So sometimes this is also called EMF, doesn't matter. It's the voltage between the ends of the rod. So B is the field being sliced through. L is the length of the conductor. It has to be a conductor because the electrons have to be able to move. And V is the speed at which they're slicing through. So for example, if you take a 747, which has the wings that act like a huge conductor, and you fly over the North Pole, you're slicing through the Earth's magnetic field, and you will induce a voltage between the tips of the wings of that airplane. Okay, now an application of that BLV is this classic question. It's actually like a rail gun. If you put a conductor on conducting rails, immerse this in a magnetic field, pull this to the right at some speed V, you're going to get a voltage between A and B that depends on this length, L. And that voltage will be the BLV. And so the current, you'll induce a current in this loop. The current will be the voltage divided by the resistance, where R is the resistance of that resistor in this loop. And now the question is, which way does the current flow around this loop as you pull this rod over to the right? And this you figure out by using Lenz's law. And what Lenz's law basically says is the induced current creates a B field that opposes the change in flux. What that means is if you have a loop of wire and let's look at this as a loop of wire. So this up here, around, down, across, there's a loop. It has 4 magnetic field lines in it. And so it likes to keep 4 magnetic field lines. If you try to change that, so if you pull this rod over to the right and introduce more magnetic field lines into the loop, it doesn't like that. It's going to induce its own current to try to oppose that. It's just like friction. It's always trying to oppose what you're doing. So if this move. So let's do this. Okay, so here's initial 1, 2, 3, 4 lines. I move it over and I've got 6 lines now. Well, it doesn't want 6, it wants 4. So what it's going to do, it's going to induce a magnetic field to produce dots in to cancel out those extra X's. So this will be a dot, there'll be 2 of them. So this will be the induced field. It tries to cancel the X's. Now, the way you figure out which way the current goes, put your thumb in the direction. So put your thumb into the page. Your fingers, sorry, the dots, they point out. Your fingers go counterclockwise. The induced current would go this way. So these are your fingers of your right hand. And the induced field, that's your thumb of your right hand. And so that's how you know which way the induced current will go. It will be counterclockwise. And in the videos on mastering physics, they have some good examples of this. Another good example of this is if you have a solenoid. So let's say we have this solenoid like this. And there's a resistor here. Now that's a loop of wire, but there's no current in that wire. It's just sitting there. And there won't be any current unless you do something. And so the way that you do something is you take a magnet here. And you have, now if you just put the magnet there, nothing's going to happen. You have to move the magnet, because remember, out of this magnet are coming magnetic field lines like this. B. So when it's stationary, there is no change in flux. Remember, it had, the EMF is proportional to a change in flux. You have to change the magnetic flux in the loop, or you're not going to get anything happening. So a stationary magnet here, nothing's going to happen. Now, if I move it into this solenoid, suddenly now the magnetic flux lines are increasing. I've got all these lines going over to the left. Well, the loop doesn't like that. It didn't have any lines to start with, so it's going to try to oppose those lines that you're introducing by pushing this magnet in. And the way that it opposes it is it produces its own magnetic field opposite. Let's see if I can get some color here. So opposite to those ones you're putting in, these are going to be, this is going to be B induced, trying to negate what you're doing. So now to figure out which way the current goes through the resistor, because that's the question, put your thumb in this direction. Your fingers curl around the solenoid. So you put your thumb over to the right, fingers curl, loop around. The induced current would go like this. Go up underneath the solenoid, around, 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 back this way, and then over to the right. And so that would be I induced. Okay, and that's what Lenz's law is all about. Okay, so that's probably enough for now.